So, welcome everybody. So today we're going to talk about undefined behavior. I will be your guide. My name is Piotr Padlewski. So we're going to talk about what is undefined behavior, why it sucks, and how to fight with, like how to mitigate issue and how to find undefined behavior, and like why do we actually need it?
I thought it was awesome.
Yeah, it is.
But now you're saying it sucks.
I mean, you know, it sucks, but it's awesome. So what is undefined behavior? So basically, C++ standards say there is no restriction on the behavior on the program. But when does it affect behavior of our program? So it only affects if we actually execute the thing, or if the compiler knows that we would actually execute it. Okay, so it's not like basically if we have let's say that code, like a block, let's say if false, and we have some undefined behavior there, then it should not affect behavior of our program. And the most important thing is that compilers treats undefined behavior as a promise that these things are not going to happen. So, what can really happen after hitting undefined behavior? So, you probably heard about these little creatures that come from your nose and mess up with your code, nasal demons. But, like seriously, like in theory, you know, everything could happen, right? The standard does not guarantee anything. But you know, the odds of formatting your hard drive are zero, right? It's like it never happens. Like who did format hard drive using undefined behavior? Like no one, right? Of course, I will get into the examples when it actually happens. So let's start up with some boring undefined behaviors. Oh, by the way, if you have any questions or any comment, just like do it on the way, right? It's better just wait till the end. So, you know, there are things like naming variables starting with double underscore, or defining functions in namespace.std, or like specializing non-user defined type in namespace.std. So like translating, it means that, for example, we cannot specialize std hash of pair of integer and integer. If it would be a hash of pair of my type and integer, then it would be fine. And other thing, we cannot take address of member function from namespace.std. So you know this sounds like pretty weird. Like why behavior of my program would be undefined if I use some weird names for my variables, right? And there is a reason for that, because like suppose that you would define a macro, and then you would include stud vector. Like if the name of the macro would be the same as, I don't know, some parameter or like some part of the name inside of the implementation of the vector, then you might actually change the behavior how the vector works. And in most of the cases, if you would actually do this, then you would get either a link error or a compile error, but it's not guaranteed, right? So the standard needs to have some sort of namespace where it can put things, and it can just guarantee that this thing, like this will work, like as we said, right? And it cannot just say like, okay, if you, I don't know, do this, then like it's not gonna work. Like this is basically undefined behavior. And like the same thing for namespace.std, like the putting functions in namespace.std. So if like there might be some implementation, like some like helper functions that implement some things. Like we don't want to violate ODR and things like that. And it's also about being. It is also about the new standards. So if we will, let's say, move to C++20, and someone will add a new member function, like I don't know, someone will add a new pushback, like standard did in C++11, then if you actually take address of pushback, and like multiple people did it, like, I don't know, using boost bind or something, then it won't gonna compile, because now we have two definitions, right? And this is because like this is totally valid, because like from the standard point of view, like, I mean, it is it was invalid to take the address, right? So then standard can break things like that. So how to mitigate those issues? Like, there are no good techniques, but it is not a huge problem. So no one wants to deal with this, right? It's like, who uses ugly names like starting with double underscore? Only standard libraries. So we could use, for example, clang tidy check that would check for the names, but yeah, that's not a big deal. So let's go to some more interesting undefined behaviors, like calling main, or integer overflow, or using uninitialized values, or forgetting return statement. So what's up with calling main? This program is totally valid in C, but it has undefined behavior in C++, because you cannot take address of main or call it or do anything like that. And the reason for that is that we don't want to have we don't want main to be recursive, or in other words, we don't want to we only want to have only one call to main. Like, there is only one start. Like, just on the beginning of the of your program, main will be called. And the reason for that is that, let's say you have like multiple global objects and they have initializers. So then by like running those functions, we can actually figure out what will be the values of those global objects and then like forward it to the main, right? So then we can do a const propagation. But we couldn't do it if main could be called multiple times, because we wouldn't have this assumption that will be the values of the main of these globals. So overflows. If we compile this function, then a smart compiler can actually do transformation like this. And this like seems totally valid, right? We have like just by doing simple math, like we always know that x plus 1 is greater than x. But this is not the case if we have unsigned integer, because the unsigned overflow on unsigned integer is totally defined, right? We just have to do modulo. And overflow with the signed integer is undefined. So this means that compiler can look at it and say like, okay, if x plus 1 would overflow, then this would be undefined behavior. So there is no way that it can happen. Like, this is something that cannot happen. So I can go like, I can assume that it's not gonna happen. So by doing this means that x plus 1 will be greater than x. So I can just replace it with true. Or there are things like if we multiply and then divide, we could also just forward it to x. And there are multiple bugs with this, because many people did check if the overflow occurred just by doing a computation like this, right? Like, let's say that you want to, someone passes you a size and you want to allocate size plus 1 because you want to put, I don't know, 0 at the end. Then some people checked if actually, like, if size plus 1 overflows and then would abort or something. And smart compiler can just delete the whole branch here, right? So there were multiple bugs like that. But actually, integer overflows is not very helpful for that cases. Like, I don't think it gives like a lot of performance from deleting branches like this, because this is more about loops. So if we take this kind of loop and we will ask Java, like, what do you know about this loop? Like, Java compiler probably will not be able to tell you that, for example, this loop will terminate, right? Because the integer overflow is defined in Java. So it can as well just, the n could be the maximum value of the integer. So it could just wrap and go, right? And won't terminate it. it will know that this loop will have n+1 steps, or that n is always greater than I. But there is also something else that is much more important. So if you have a signed integer, and we do some address computation, like here we do a sub I, b sub I, and we are on a 64-bit architecture. We have to compute it in 64 bits. And basically, if this will be unsigned, we will need to have some extra instruction called zero extension. And it would be much slower, especially if like this loop would be pretty hot. So, and because we know that the overflow cannot occur, then we can just widen it to 64 bits, and it will work. So with all those cases, you know, vectorization and unrolling is basically much simpler. Like probably for most of the cases, it would be possible even with unsigned integers. Note that here we use less than equals, right? If it would be just less with unsigned, then we also would be fine. So how to mitigate those issues? So UBSAN can find overflows during runtime. UBSAN is Undefined Behavior Sanitizer. It's a runtime tool. So basically, it adds some checks to your code. Like for example, for integer overflows. And when something bad occurred, it just shows you warning, or like it shows you error during the runtime. There is also flags to GCC and Clang, like fwrap, which define integer overflow. So if you're not a fan of undefined behavior, you can use this flag, and like compiler will not perform optimizations based on the undefined behavior from integer overflows. And there is also ftrap, which basically traps on every signed integer overflow. And sometimes warning can also help. Okay, so let's move to the uninitialized values. So if you think that this function is a random number generator, then like, seriously. So because if you actually call this function, and optimizer will just see like, oh, okay, I am just reading an uninitialized value, then it can translate it to this, right? So like I don't see this as random at all. And like many people, like there are some cases in an open source project or some big projects where people used uninitialized values as an input to random number generator, right? And like it worked for some time, but then the new compiler came and see, oh, that's funny thing here. So I would just optimize it away, and it wasn't random at all. So how to mitigate those issues? Pretty much like warnings helps a lot. Static analysis can help. UBSAN I think can catch some of the cases, and there is also a tool called Memory Sanitizer, and this tool is designed to catch reading of uninitialized values. And like for simple cases, like if we have just a small integer, it's pretty easy for a compiler to find out that it was not set. But if you have some very huge buffer, then it is like you probably cannot do it in a static, like during a compilation. You have to do it in a runtime. So with that, let's try to answer some questions. Like for example, I think that something is a good candidate to be undefined behavior, like in C++ standard, when it would be considered as a bug, and we would lose some performance if it wouldn't be undefined behavior, right? Because C++ is about performance. Anyone agrees with that? Okay, a few people. I will try to convince you. So I'll try to give you some real reasons for some undefined behaviors. Like for integer overflows, it's like back in the days when C was there. like some architectures did weird things when there was assigned integer overflows, right? It could trap, it could behave like as the CPUs that we have, like that we use today, or it could saturate. There is a different things, and standard couldn't say that like this one thing will happen because like some CPUs might like it would cause some CPUs to be slower. So it just didn't define it. And there are things like initialized values where we pretty much like setting up one variable is pretty fast. Like we just do XOR or something. But if you have a long buffer, then it actually might cost us a little. So also, so this is why I think it's not defined. And the things like dereferencing and null pointer. If you would like to define null pointer dereference, then we would actually have to check for if just before the referencing, if it's a null pointer, and then raise exception or something, right? So because like some architectures could implement it in a better way. Like for example, if you read from memory 0, then there is a special page that fails, things like that. But basically, like standard couldn't just define it because there might be some platforms that wouldn't work. And for things like a buffer overflow, we would have to do a bound check, and it's also like pretty much not possible with the pointers because you might just get some pointer, and you pretty much don't know what's the bounds of the memory that it points to, right? So it's not that easy. So let's move to some tasty undefined behaviors. So here we have a null pointer dereference, buffer overflow, using pointer to objects of ended lifetime, violating strict aliasing, and const casting const. Okay, so this small program contains undefined behavior. It contains a really simple bug. Who sees that? So we have use after move, pretty much, right? We just move from P, and then we dereference P. And unique pointer is totally defined, like the move constructor of unique pointer is defined as setting a 0 to the pointer, okay? And this is actually not a thing for every container, like stud vector. If you move from vector, then they are only saying that it is in a valid state, but it doesn't mean that it is as you would just create a new vector. In order to use vector after moving, you would have to actually call clear or something. But this is not the case for a unique pointer. So here we will have the null pointer dereference. And when you compile it with Clang and run it, like you actually get something like this. So it just, let's state the fact. Like my compiler is an also, right? It's like it just saw the undefined behavior in my code and like deleted my whole code, right? And so let's see how it worked. So just after doing some inlining, it found out that we are doing a null pointer dereference. So it put it something like called unreachable, which means that this path is not reachable, right? And everything after unreachable is of course unreachable, so we can remove that. And now we can just do some simple optimization, like P2 is not used, P is not used, we don't need allocation, bam, it just deleted the whole code. And we were pretty lucky here because we got it emitted a trap, right? So our program did not like silently close and didn't say anything. It just crashed. So we were lucky at least for this one. But there are some other things. Like in that case, we just had a null pointer dereference, right? And here we don't have any null pointer dereferencing, right? But if you compile it with GCC, it will see that, okay, so we are dereferencing a pointer, right? And then we are checking if P is a null pointer. So if P would be a null pointer, that would mean that the the reference was invalid, like it was undefined behavior. So it cannot happen, which means it's false, right? So you can just delete the whole thing. And there are many bugs like that. Like, for example, you could put a printf or something, as John showed yesterday, to, I don't know, debug a value, but you forgot to put the if statement. And then because you just called printf and you've loaded the value, then all the checks for the null pointer will be deleted after this. And you might say that, okay, but, you know, like not many people write code like this, right? And you are probably right. Like things like this happens mostly after inlining, right? So because if you have a function and we have check like that, then like it might be a dead code on some branch on some call sites, but it doesn't mean that it's dead code like on every branch, right? So this is also a reason why it's not that easy to find things like that. But wait, there is more, because what is better, like removing your code forward, right? Who knows what I am talking about right now? Any guesses? Time travel. So let's move the check above, right? We first will check if p is a null pointer, and then we'll do some things, and then we'll dereference. So if the compiler will be smart enough, it can actually do this. Okay. So let me walk through how it could happen. So we know that on every path we're gonna go to the pointer dereference. So we might as well just copy it, like hoist it to the branch, and then do else, right? It is the same equivalent program. And then it could see that, okay, but we have a check if p is a null pointer, and then we dereference that. So this is unreachable. And then, like, if this is unreachable, so it means that we cannot, like, this part of the code cannot be reached, which means that this thing also is unreachable, and the whole branch is unreachable. Okay. So, you know, for me, it looks like that, right? It doesn't. You know, it seems to me that this is kind of optimization that does not play a big role here, right? Yeah. But there are some more stuff. You probably might have seen this example. It was pretty popular a month ago or something. So we have a function pointer, and we call it inside the main, right? So this is a global thing, so it is set to 0. And we also have a function set that sets this pointer to evil function. And note that evil function and set function is never called, right? But there is one thing. This function pointer is static. This means that the visibility of this is only this translation unit. So this means that compiler can come up and say like, okay, I can just see all the reads and writes to this pointer, right? And I know that like this is set to 0 in the first case, and here like it will be undefined behavior if I would just read it from 0. So there must be some way that like this function pointer is set, right? Like I don't know, some global initializer or something. So it means that I actually have to call this function, right? Because like the function set needs to be called somewhere because it will be undefined behavior in other case, right? And as you can see, now function set does not do anything, right? It just returns, and we just inlined evil function to main, right? And as it turns out, this for some benchmarks is actually a pretty important optimization. Like maybe not with the function pointers, but if we see that we write to a global variable like the same constant all the time, yes?
Would this still be undefined if set was static?
Yeah. I mean, like pretty much the same optimization would happen. Yeah. I mean, it doesn't matter if the set is. I mean, like maybe compiler could figure out that set is never called, but like it can do it could do the same thing like anyway. So yeah, so if there is a global variable that we set the same value all the time, then for some benchmark it actually matters to like find out that okay, we are writing the same value, so you can just const propagate it for every read. Okay, so let's sum up the referencing and null pointer. So first question is like why the compiler does not warn about these things. Like it is clearly able to find those like those optimizations and perform it. So why it does not tell us about this, right? And one explanation is that diagnostics are much harder than optimizations, because in diagnostics you have to think about false positives. So if we have this thing in another function, like just after inlining and finding out that this branch is dead, this does not mean that this branch is dead for every call site, right? So if we would just raise like warning, like we do some weird things here. It's like, or like the set function, like this is dead. It will be invalid, right? Because there might be some other function that calls it with a p that is a null pointer, and it will be totally valid. The other explanation is that there is compiler architectures like Clang issues diagnostic in the front end, and it is doing optimization in a middle end. And in a middle end, we lose a lot of information about code. And it's like, first it will be pretty hard to go back and like issue a warning about like special line of code after doing a lot of optimization. And also we have to do inlining, so we will have to keep track of what we did inline and stuff like that. So it is not really simple. And there are also some other compilers like MSVC that actually issues diagnostics in backend. And this is also pretty weird, because depending on what optimization level you are using, you'll get different warnings, because compiler will figure out different things, right? And other explanation is that we don't want to repeat the computation, because we might as well just like do the same things in a front end, and then do like pretty much the same, use the same algorithms to do the optimization in the backend, but it would take time. How to mitigate dereferencing and null pointer? Firstly, like try to not debug with optimization. Like if something weird is happening into your code, like it might not make sense to debug your code with optimization turned on, right? Because if the optimizer figures out that there is some null pointer dereference and it will just delete your whole code, then we're gonna have a bad time debugging it. So if you just don't use optimization, you will be fine. There are also some flags like OG, which is please optimize it in a way that it does not affect optimizations. Sorry, it does not affect the debugging. This some like sort of work. Like I heard some complaints about like that it doesn't work all the cases very well, but there is something like this. I think Clang is trying to have it as O1, but there is not a lot of work going on with this right now. We can also use static analyzers. So in my opinion, it would be very nice to have some sort of flag saying that like please don't perform some weird optimization that's like that will be very hard to debug, or like please don't perform very weird optimizations that I don't care about. Okay, so let's go to the return statement. So in C++, when you forget a return statement, then there is a path in your function that leads to like end of the function without the return statement, and we have to return something. And this is undefined behavior. And compiler can pretty much just optimize it to this thing. Because right now it just assumes that P is always true, right? Because if P is not true, then the path will lead to undefined behavior, which is undefined, so we can not think about it. But pretty weird things can happen if we actually like don't have any return statement at all. Because what clang will do for this one is that it will emit some instructions, and it will forget return statement at all. Like you won't gonna have any return in your function in assembly. And so if you actually call this function, like it will just start performing those instructions. Like I don't even know why it did emit this push. But anyway, it will start to do these instructions, and then it will just go on, right? It might find some other function or something else. So this sounds like a fun. So what if there will be a pretty weird function just after it, by accident, that is never called? So, like we could get the assembly for this function just after my function, and if I will compile it on my machine, and I will call function foo, this won't gonna work. Like it won't gonna format it won't gonna delete my files. Why is that? Like, does anyone knows? Any guesses? I'm using 64 bits. Sorry?
It's not aligned?
Yes. So in 64 bits, like x64, the stack needs to be aligned 16 bytes when we call the function, and we do a code to the system here. So and yeah. I mean, it just crashes pretty much, right? Probably like the system does like, I mean, probably there might be things like that care about those. Like there is no probably there are no checks for this, but I don't know. CPU may assume the alignment. I don't know. And because of course we are doing this one push, it is only pushing or 8 bytes. It is unaligned. So we can fix that in simple way. Let's add some other function. And if we like compile these two translation units, it will work on my machine. Like if we call function foo, it will just delete all my files. I haven't checked that with the RM, but okay. So to mitigate those issues, like pretty much, I don't know, read compile warnings. Like I cannot tell you more of us. So the other thing is that it would be nice if Clang would not screw up with us like this, right? It's like it would be nice if it performs optimization like this. It would, I don't know, emit a trap or something that would stop running on other functions. Yes.
So is Clang actually seeing this as an advantage? Because I will freely admit I've made this mistake.
Mm-hmm.
I have forgotten the return statement. It is painful to debug.
Yes.
And it's not repeatable. So they're thinking that that's what you intended to do?
So I also had this bug, and like it's always like I am just debugging, like, oh, there's some warnings, like I don't care, right? And then like what happens, right? So I think it makes sense for some cases where, I don't know, you have where you don't have this kind of like you have some paths, like I don't know, we have a switch and there is some unreachable block or something. Then it might sense to do some sort of optimization. But yes, like, yeah.
Doesn't Clang warn by default if not all control paths return a value?
Yes, it do.
Yeah, it's warned. But even when it's not an error, I thought it'd be like, well, it should be an error. That's an error.
I don't think so. I mean, maybe it changed, but like at least, I don't know, 2 versions ago or something.
W error.
Yeah, of course. But like, you know, it's like if it's, you know, not everyone is using these kind of things, right? And yeah. So let's move to some more interesting stuff like buffer overflows. So this simple code also has undefined behavior. So we just have a function that it just checks if we have a value inside our table. And we have 4 elements, and we go from I equals 0 to 4, and then we dereference, right? And because it has only 4 elements, and we actually go to the 5th element, then this is undefined behavior in the last step, right? Like someone just should put less or, instead of less than equals. So then compiler can come and see like, okay, I would just, this is it is a constant count, so I will just unroll it, right? And then it says that, oh wait, like in the last if, there is undefined behavior, right? I'm just going out of the scope. So this is something that cannot happen. Like I'm probably finished my working like before it, right? So, and like the only way you could finish the work before it is by finding the element, right? So we will just return true. So now we have a function that if we carry with like any integer, like pretty much our table consists of every integer we can think of. How to mitigate those issues? So we have others sanitizer and we have Valgrind that pretty much like it's designed to find buffer overflows. And of course, this won't gonna help us if the compiler will optimize it away, right? So another thing, like don't like if something pretty weird happened, just like spend a couple of minutes recompiling with debug like without optimizations and then start debugging. And also like static analyzer can find some sort of issues like but of course it usually is not that strong to find in most of the cases. So let's talk about const. So here I have some implementation of my vector or something, and I have function size that is const, and I have operator square bracket that is also const, right? And of course, const means that I won't gonna modify anything in my class, right? So is it legal to do this kind of thing, right? I'm just iterating over my things, and I don't modify anything inside of the vector, so the size shouldn't change. So can I just hoist it and not call size every time?
No.
Yeah.
No. Size could return just a global variable.
That's right. And besides this, like const does not actually say that we cannot modify anything inside of a class, right? So this is invalid. But it actually works with the standard vector. So if we write something like this, it will pretty much optimize it to this kind of thing. Any guesses why it works with standard vector?
Size is inline.
Yeah, it's pretty much inline all the things, and like by magic of compilers, it is able to figure out that I just have those pointers. Like the size is a subtraction of this pointer from this pointer, and I do not modify those pointers, so it is constant, and I can hoist it.
Sorry,
Yeah.
what was the problem with the first code block again? The one where you set size before.
This one? Yeah.
the one
Okay. So we cannot compiler cannot transform this one to this one. Like it.
Oh, okay, yeah.
Yeah.
The code is fine. It just can't transform.
Yes. Yes. And there is another thing. If you actually write a for loop like this, it will pretty much do the same thing, because if this range-based for loop actually memorize the beginning and end, so it does not call like end all the time in the loop. This also means that this transformation in your source code may not be valid all the time, right? Because if you actually modify vector, like if you push back to the vector inside of the for loop, you cannot just use the range-based for loop for the vector. You could use it for a list or something, but you also wouldn't get all the elements if you push back to the list. Okay, so about const. So it is pretty much illegal to do this kind of transformation because the size could return a global, or even if we would return like a member size or something, we could still const cast. So const cast on the const reference is like it is about what the reference points to. So if you have a const reference or like const pointer that points to some memory that was not declared as a const, then it is legal to do a const cast. If we have a const reference to a variable that was declared as a const, like let's say I have a const integer, then this is undefined behavior to do a const cast. Okay, and like the pointers and the reference is about like how I can get from point A to point B. It does not guard us from like actually modifying the thing that it points to, even if it's a const reference. So pretty much like const does not help us with any sort of optimization like this, right? Like maybe if we declare a variable as a const, then it could help. But as I see, I think compilers, at least for like non-global variables, does not perform like any major optimization there. What's the solution to how to fix that? Use link time optimization, basically. Like we don't actually need to have this guarantee in C++ if we do link time optimization, right? Because like you may think about, okay, what if a const would be actually stronger and do this kind of thing, right? So let's just introduce a new undefined behavior. But we actually don't need to because we have the tools to like avoid these kind of issues. And you might say like, okay, but do I look like someone who has like a lot of RAM and a lot of, I don't know, CPU power? Like link time optimization is so slow that like no one is using it, like seriously. But there are some other good things like FinLTO, which is a new framework for scalable and like fast link time optimization in LVM. There is also WOP in GCC, and there is LTCG in MSVC. So there are alternatives, and like they works pretty well. Okay, so let's talk about the lifetime of the pointers. This is slightly modified example from John Reger blog. So I have so I allocate memory for one integer, and then I reallocate this memory. So this should return me the same pointer because like I didn't pass any bigger size. It is the same size, so I can like reallocate and return me the same pointer, right? But just to be sure, I will check if p is actually equals to q, okay? And then I will write 1 to p, I will write 2 to q, and I will just print those two values. And if you compile it with Clang, you'll get 1 and 2. So like, you know, I have those two pointers pointing to the same value, and the value of one is 1, and the value of second is 2. It doesn't make any sense, right? And this is like totally valid optimizations to do because there is undefined behavior in our code. And undefined behavior happens when we dereference a p. So here, right? And this is because if we reallocate a memory using realloc or a placement new, then the old pointer is pretty much dead. You cannot use it. It points to memory that is dead. And even if you have a pointer that points to the same memory, like there is some magic going on there, and that says that pretty much like that pointer is invalid to use, but this pointer is valid to use. So you can use q, but you cannot use p after doing realloc. So, is there any difference between virtual functions and functions like virtual functions written in C, right? Because like you probably have some like colleagues writing C code, and they're like, oh, I don't need C++, I can write virtual functions by my own, right? But actually, C++ virtual functions can be faster, okay? Because like assuming we have the same semantics of the virtual functions, and we don't do some like tricks that C++ does not do, then the compiler can perform more optimizations on C++ virtual functions. And it comes to the object's lifetime. So if we have a virtual function, right, and we call the same function 2 times, that is really called the same function. Like we would probably expect that this is the same function. Like what can happen there? Like I mean, like is there any magic that can happen in a virtual call that would change a v pointer or something? right? And like, what about this? So there is some magic called placement new, and this line is pretty much what it's doing is that, okay, I will nuke myself, like I will create an object of type derived inside of myself, and as long as derived is the same size as type base, this is valid. Okay, so like this line is legal thing in C++. You can write evil code like this, and this is not fun for me because like I work on a devirtualization and I have to care about cases like this. But there is a good thing because there is object lifetime. So if we actually nuke ourselves with placement new, then the pointer that we have to the old object is a zombie, right? It is invalid to use. So this means that after this first call, like if this function will be called, like the second call will be undefined behavior, okay? And compilers that does not use this fact right now. There is a implementation in Clang with like f-strict vtable pointers that uses this fact, and you can do the devirtualization like this. But in general, it's very hard to actually to have a model to model const like this in a C programs or in C++ programs, and that's why it's not still in on default, because there are some weird counterexamples that we miscompile. How to mitigate this kind of issues? So I mean, like nobody is nuking like v-pointer inside of the virtual function. But there are some other things, like someone could overwrite v-pointer by a buffer overflow or something. So there are things like control flow integrity, and this is a Clang thing. I think there is also another thing in MSVC. So what the CFI is doing is that for every indirect call, it checks if we actually called some function that is some kind of valid, at least like if we don't just call some random memory or something. There is also ubisan that checks if we are calling a function that like it just goes to the the runtime type information and checks if the type information is the same as like my v-pointer, and if not, it just issues runtime error. Okay. Wrapping up, there are also some things that are pretty weird in C++, because for some cases, C++ is saying that, okay, this is totally defined, or it does not tell anything about some things. So, for example, like there is no single mention of a stack overflow inside of the C++ standard, right? Like this thing doesn't exist for C++, and this is pretty much because it is not a language thing. It is more about like the platform and about like way it works, right? And so it's like just a standard that does not care about things like that. And there's also things like throwing bad alloc when allocation fails. So if you ask like dear Linux kernel, please give me 64 gigs of memory, having only 60 gigs of memory, it will give you it may give you a pointer that is not null, and it will not throw any exception, anything. And you're like, okay, I have a pointer, I just have 64 gigs of memory. So I will just start reading or like writing to it, right? And every time we're gonna hit a new page, it's just gonna allocate a new page, okay? So we can have like a lot of virtual memory, but we might run out of it. So if we're just gonna just start writing to this memory, at some point it's just gonna crash, right? So this does not seem like a thing that we can catch by a try except or something, right? This is thing that like totally is like Tanner is saying like, okay, we're gonna have a like bad alloc or like null pointer or something, but it actually does not work. Okay, so wrapping up, pretty much undefined behavior is used to optimize code, right? There is a bad thing because we actually don't know what gains do we get from every undefined behavior. Like we have some knowledge about some sort of undefined behavior. There is like a couple of papers. There is of course like knowledge in the compiler writers, but there are like many things that we don't actually know if this makes it makes sense to have it as undefined behavior. Okay, and like do we actually gain anything like any performance from this undefined behavior? And like I totally think that there should be like for every undefined behavior there should be a tool that we could find it, right? So like, and I think Clang is trying to do that a little bit. So like if they do some new optimization, they like trying to make sure that there is a tool that like may actually find this kind of sort of problem. Like if we do optimization on undefined behavior, of course it is not perfect. We have those like runtime tools like ASAN, TSAN, like UBSAN, things like that. So some other flags, but pretty much it's like it is not complete, right? We are getting there, but yeah, it will probably take a lot of time. So unfortunately, undefined behavior stays in C++. So, thank you for your attention. And do you have any questions for me?
Hi, thank you for your talk. I want to share a particularly awesome undefined behavior we had in our company. We had a loop that would try to connect until a certain amount of retries. And the loop looked like this. While P and retries minus minus, P equals connect. Okay. So that sounds fine. Somewhere about 20 lines later, or something like that, in a completely separate place, P was accessed. Can you imagine what the undefined behavior logic did there?
Wait, so there was like, what does the end means? Like?
While P, while not P, I'm sorry.
Okay.
While not P, meaning haven't connected yet,
okay.
and retries minus minus, meaning retries hasn't hit 0. P equals connect.
Okay.
So it would return null if it didn't connect, or it would return the thing if it did manage to connect.
Okay.
And you do retries 5, 4, 3, 2, 1, 0, and then leave the loop.
Okay.
So P was accessed 20 lines later.
Okay, so you actually, so you mean like you could have a situation where it actually like didn't work, like the connection didn't occur, but you actually dereference a pointer after.
But you still dereference the pointer.
Okay.
So the compiler, in its infinite wisdom, removed the retry check.
Okay.
It did not remove the P check, because that is the right thing. That is not what you would expect. You have a dereference of a P, and the undefined behavior deleted your retry check.
Yes.
So
yeah.
that is, I think, a particularly nice,
that's good example.
awesome undefined behavior.
Yeah. Okay. Any more questions? I unfortunately do not have any backup slides. So. Okay, so thank you.